Creating just to try to make the day before a test. I wanted to reach out to some people on Zoom and we weren't able to get in, so this is just, I just want to talk about a few quick problems here. Basically 27 and 45, because it's a kind of problem where a lot of what you're learning in 27, even though 27 is kind of brutal the first time you go through. We're going to look at 45 here first, because 27 is basically just a little bit more complicated version of 45. And so 45 is, they have a slide where somebody is starting at a specific height, capital letter H. They're sliding down and they exit horizontally at a height of lowercase h. The difference between this and number 27 is that the girl that's going down the slide actually goes up at an angle, and you have to find the max height she is. So that complicates things, but the basic of how you would set this up is similar for both of them here. So the first thing we need to do, and this is the very helpful, is we have to think about if we can write an equation for the energy anywhere on the slide. That is the equation basically the energy everywhere. So for example, say, hey, how do I create an equation for the bottom or the middle? Look at the top, because if you look at the very, very, very top, the person down the slide is not moving. And if they're not moving, there is no kinetic energy. So your equation is only gravitational potential energy, which is mg times big H, because you're up the top there. So here's the realization that you can use this energy as your total energy, because at the top, you only have mgh, and that is equal to your total energy. So that means, since total energy doesn't change in a isolated system here, that anywhere along here, including the bottom, is equal to mgh. Now, there's equations here, but you can set the two equal to each other. At the bottom, we have kinetic energy because it is now moving, so 1/2 times mvi. They use VI in the book because you have to calculate a trajectile here. So it's your initial velocity when you exit the ramp. That's why it's VI. So you have your kinetic energy, which is the 1/2 mass V squared, plus whatever your potential energy is left, because you're not all the way down at the bottom. If you're all the way down at the bottom, there is no energy. And here we have mg lowercase h. This is our equation right here. And we have to realize, if we want, what we're trying to do here is we're trying to set up what is H, basically what is big H, how high do you have to be up there in terms of D and H only. And you're thinking, what equation do I have? Or sorry, when we go over what D is. D is this distance right there. Or as a projectile, it is your horizontal distance, it's your range. So in terms of how far horizontally it goes and the height at where it launches, how high does this have to be right here? So this isn't in order at this point, but realizing that what we can do is we can set the two equal to each other here. So let me get a blank paper here, that the energy, total energy there, mgh, is equal to the total energy at the bottom, which is 1/2 m initial velocity when it's launched from the slide, plus the gravitational potential energy at lowercase h. Now we can only have an equation with D, big H, and little h. So here, mass cancels out. I'm going to go ahead and rearrange the equation real quick. So to solve for h, it's not this symbol. There's a lot more work we have to do. But it's 1/2 VI squared over G, because you G for there, plus you divide both sides by G. Let me do it this way, sorry. 1/2. And then you divide G over here, and it cancels that out, so plus H. And interesting enough, that H is going to stay there. So there's where our H is. We need to figure out what is this velocity here required. And this is where we use some projectile motion problems. Now, it's simpler than number 27 because it's just a horizontal launch. And that's nice because there's no components of the velocity. in the, I guess there's no components in the velocity initial direction. So in the x direction, I was kind of doing this here, let me refocus it here. In the x direction, we have our velocity. The velocity in the x direction is how far it moves, distance over time, or delta x over t, how we might have used it here. So when I solve for time, I get the distance over the initial velocity in the x direction. So that's important right there. We're going to keep that. In the y direction, there is no initial velocity in the y direction because it's a horizontal launch. The angle sine at 0 is 0. So VIYT, in my class, this was the third equation. Delta y is just this height here. And we'll go ahead and use positive, so that's positive. But that goes to 0. You have delta y equals 1/2 gt squared. You rearrange that to solve for t, and there's your equation right there. And so we need to now, here's the thing, we talked about this in my pre-physics classes. The one variable that doesn't have a direction is time. And so those two can be set equal to each other. You do a little bit of algebra. I'm not necessarily going to go through it here. I need to get VIX, so I'm basically going to invert both of these. Let me go back a little bit here. Okay. I'm going to invert both of these. The camera's running slow. Flip that upside down to get to here. And then I solve for VIX, and this is my equation for VIX. So what you're doing is you're plugging that into that right there. And I have it over here. I have messing up a couple times. That's okay. I was just like, I can't do math. So here's me doing that. Here I cancel out the m's. I plug the value of VIX in there. It is squared because it is kinetic energy. When you do that, D becomes squared. Let's see here. Yeah, D becomes squared. G stays on top. 2H goes to the bottom. This 1/2 eventually becomes 1/4. And then G's are in all of them, G, G, and G. And so those cancel out. And you're left with 1/4 D squared over H, small h, plus H, or written down as that. And so that's a lot. Let's break it down again. How do we even get this equation right there? And it goes back, and this is really important here, that the total energy at one place has to be equal to the total energy of other place for the isolated system. There's no friction, and by the way, there's no friction in this problem here. So this is the bottom. This is the total energy at the bottom. I don't know how you use, and that's the total energy at the top, and those things have to be equal to each other. And so we have an equation for the total energy in terms of the height of the slide at the very beginning, and we have the total energy in terms of the speed and the height of it at the very end, and that is really good because that gives us enough information. The last thing we did is like, we need to figure out what that velocity is, and we use some kinematic equations here to solve for what the velocity would be, and then plug it. It's just about simplifying. One of the reasons I love physics, especially when you solve things in variable form, is that things that you think would certainly matter end up not mattering at all. Commonly you see mass not matter, which is also something interesting. So that's 45. I'm not going to go over 27. It's just really long, but basically the setup for 27 is that same thing, that the total energy at the top of the slide or the top is equal to the total. And that's not just for slides. You're like, well, that's specific. That could be for a pendulum. That could be something that's swinging. If you know the height of what it's swinging and you know the height at what it's here, you can use the same equation. Like if it's a pendulum swinging and it swings, so at this point in the pendulum cycle, it's maybe a meter off the ground, and here it's like 5 meters off the ground, whatever happens to be, you could still solve for how fast it's going to be going, and if you know how fast it's going and the height where it leaves, you can figure out how far it's going to go. I believe you did this in your lab with the ball down the ramp, and you're trying to predict how far it's going to go. This is what it looks like in actual variable form. The other things I wanted to mention here are some things about power, because we were working yesterday, and power, there's a couple equations. I don't want to say memorize equations. You get an equation sheet, but there's a couple equations here. So for power, yes, it is work over time. It's the rate of work being done. Work is force times distance divided by time. But you have to be careful because sometimes the problem won't be giving you force. Like this is like some marine that's going up some stairs or whatever, going up on a rope or something. So they give the weight of the marine. But what if they just gave you the mass of the marine? You would have to figure out the force of gravity or the weight by multiplying times 9.81 times the distance, 12 meters. He's moving in the same direction as that, divided by the time. So any of these three are helpful. The other really helpful one for power is FV. This one is about a car. It's saying like a car has 175 horsepower, and you're having to figure out how much force what is the amount of force of friction due to the tires on the road that is producing this speed, even though you have this much power. And so they give 175 horsepower. The conversion, I think, probably will be given. That's the amount of watts. And power, if you hear force and power, you want to be thinking about work. You're saying, where does FV come from here? Well, isn't V just distance over time? Isn't V just D over T? So F times V, sorry, this video is moving a little slow here. P equals F times V. Quick right here. Yep. Oops, sorry. F times V, and we can rearrange it for F. We know the power output of the car, and we know the speed that it gives. They give us that we're going 29 meters per second down the highway, and you can calculate the force of the friction because it's doing negative work on the because it's removing energy from the system, and that's how you figure that. So P equals F times V, very, very, very helpful. Last problem we're going to go over real quick, and this is a power one where we're sort of using some net force equations. My computer's running low, so okay, let me shut some things down right quick. Probably don't need to be running that right there. I don't think okay, sorry, my computer is about to shut down. Anyway. Yes, it feels like Windows 95 all over again. Okay, okay, I think that got better. Anyway, that's what happens when you're running three browsers. Sorry for listening. 38 is talking about, when we refocus it, it's talking about an elevator that is moving up. You have the mass of the elevator. It's moving upwards. You have the force due to the motor, and it's not that it's positive distance. I rewrote that. It's that your force is going upward, and so that is producing a positive work because it's moving in the same direction. It's parallel and moving in the same direction as which way it's going. So that's a positive amount of work due to the motor, this motor here, of the pulley. And then you have force of gravity, which is down, which is causing negative work because it's working to slow you down or to in the opposite way. So what we're trying to figure out here is we're trying to figure out how much power is needed here. But before that, in order to figure out power, we need to figure out work. And that's why I brought up work here. Once we know the total work being done, they're asking for what is the power, the motor. And here we go. What is that? And if we know the work done by the motor and the time it does it, and they tell us that, then we can calculate the power of the motor. So the equation we have to realize here is that this is the work kinetic energy theorem. The total work is equal to the change in kinetic energy. Now I can simplify this that it's not 1/2 mv final squared minus 1/2 mv initial squared because there is no, it says it starts from rest, and there is no kinetic energy at the beginning, so it's just 1/2 m Vf squared equals the work of the motor, which is a positive, minus the work of gravity, which is negative. I'm going to fill out what these mean here. So 1/2 m Vf squared, that's mg delta y, which is the distance that it moves here. That's what they use in the problem. I'm going to rearrange this, solve for the work on the motor, and this is the equation we get here. So let's look at what we know in this problem. That's always helpful. What do we know in the problem? We know the mass of the elevator. They tell us that. We know gravity. They tell us that. Or we know that. We know delta y. We do not know delta y, right? We do not know delta y, but we do know the speed. They tell us the speed here. So the only thing that we do not know here is what is delta y. And if we have they ask for if we have the initial speed, which is 0, and we have the final speed, which is 1.75, and we have the time that it takes, then we can figure out what that delta y. In my class, this was the first equation. So that's 0, that's 1.75. That's the given final speed it has after 3 seconds. And so that's delta y. That's how far it moves, 2.63 meters. So now we know what that is, and it's just a plug and chug problem. When you do that, you calculate that. Remember, we're calculating the work due to the motor. That's the work due to the motor. And then we just plug it in. This is not the only way to do it. This is the way that sort of made sense to me here. And then it happens in 3 seconds, so we get how many watts it is. But it comes back from drawing the free body diagram and understanding that the total work is not just from the motor, that the force of gravity is also doing negative work to slow you down. And that total work is equal to the change in kinetic energy. If it was moving at the beginning and moving later, then we would also have to take into account the initial kinetic energy, but it was not, which made it a little easier. We would have known it anyway. They would have told us what the initial velocity was and mass anyway, just would have made a longer equation. But we simplify that, solve for delta y, and then solve for the power. That's about all the time I have. This is during my lunch period. I just wanted to help. I appreciate it if you can subscribe. Hopefully I can stop this recording. I'm going to post this to YouTube. Please watch it. Your test is tomorrow. I would recommend that you please look at this, and I will see you guys eventually later. Thanks for listening. Mr. Dahlstrom here.